Good afternoon. Myself, Dr. Hitesh Kumar, Ranote, Assistant Professor and Department of Mathematics, Maharaja Agarsen University, Baddi. Today, I discuss the topic set theory in mathematics. Basic definitions. A set is a collection of items called elements, and it is denoted by the set 1, 2, 3, or x belongs to R, 1, x greater than equal to 5. Special sets, we refer to specific set of numbers. So often that we give them special names like set of natural number. We define the natural numbers to be n is equal to 0, 1, 2, 3, etc. So know that the set of natural number are closed under addition and multiplication. Second, set of integers. We define the set of integers to be minus infinity to plus infinity. It's like minus 2, minus 1, 0, 1, 2, 3. And the set of integers are closed under addition, subtraction, and multiplication. Third, set of rational number. Rational number means we define the set of rational number to be q is equal to p of q, where p q belongs to set of integers and q not equal to 0. If q is equal to 0, then this set is undefined, means p over 0 is equal to infinity. And the set of rational number is closed under addition, subtraction, multiplication, and non-zero division. Alternatively, set of rational number is the set of all infinite repeating decimal expansions like 7.35 is equal to 7.35000 belongs to set of rational numbers. 1.234234234 belongs to set of rational numbers. Pi does not belong to set of rational numbers. Next, set of irrational numbers. Irrational numbers or infinite non-repeating decimals. Obviously, irrational numbers are impossible to write down exactly. We use symbols to represent special values such as pi, exponential function, and root 2. The irrationals are not closed under addition and or multiplication. Next, set of real numbers. Real numbers means are all decimal expansion. The real number are created by joining the rational with the irrational. The reals are closed under all operations and satisfy the field axioms. The reals form a continuum. We use the real numbers line to represent this. Next, subset. Subset, if we have two sets A and B, then we call A is a subset of B and it is denoted by A content B, provided that every element of set A is an element of set B. So A content B means for all x belongs X, if X belongs to A, then X belongs to B. We also say A is contained in B or B is contains A to show this relationship. Equivalently, we denote A does not contain B, provided there exists X that belongs to A and X does not belongs to B. Means if we have a set A and this set has element 1, 2, 3 and set B has element 4, 5, 6, then set A does not contain set B. Means 1, 2, 3 does not belong to set B. And it is A does not contain B. Example of subset, if we have set A is equal to 1, 2, 3 and B is equal to 0, 1, 2, 3, 4, then clearly A contains B. A1, 2, set 1, set 2 contains 1, 2, 1, 2. And set of rational numbers contains set of real numbers, set of integers contains set of rational number, and set of natural number contains set of integers. Means set of natural contains set of integers, set of integers contains set of rational, and set of rational number contains set of real numbers. ABC is a proper subset of ABCD, and ABC is an improper subset of ABC. Set equality, we say if we have a two set A and B, then we call A is equal to B if every element of A is in B and every element of B is in A. Then it is called A equal B. Means A contains B and B contains A. Example 1, 2, 3 equal to 1, 2, 3, but a set A is equal to 1, 2, 3, not equal to 1, 2, 3, 4 is equal to B. Since 4 belongs to B, but 4 does not belongs to B. So this example is not equal set. Also, semi-closed interval AB not equal to closed interval AB, since B is only in AB. Operation of sets means we have a two set A and B, which are subset of a universal set. We define the following union. A union B equal to X belongs to U. Universal set X belongs to A or X belongs to B. Means if either X belongs to A, set A, or X belongs to set B. And intersection A intersection B is equal to X belongs to U, X belongs to A, and X belongs to A. Means intersection में both are common element. If we have a common element in both sets, then this element is the intersection of A and B. Complement A का complement is equal to X belongs to U, X does not belongs to A. Means A complement is equal to universal set minus set A. Example, U is equal to set of real numbers, universal set is equal to real number, and A is equal to closed interval 0, 3. B is equal to open interval 1, 4. Then A union B is equal to 0, 4, and A intersection B is equal to 1, 3. And A complement is equal to minus infinity to 0, union 3, infinity. B complement is equal to minus infinity 1, union 4. Cartesian product means we have a two set A and B and define the Cartesian product A cross B is equal to A belongs to A, B belongs to B. The elements AB is called ordered pair since AB and B are distinct if A not equal to B. Example, if A is equal to 1, 2, 3 and B is equal to 8, 9, then A cross B is equal to 1, 8, 1, 9, 2, 8, 2, 9, 3, 8, 3, 9. 8, 1, 8, 2, 8, 3, 9, 1, 9, 2, 9, 3. Next, empty set. Empty set, the unique set containing no elements is called empty set and is denoted by phi. These are some properties of empty set with universal set even. If we have a set A, then intersection of phi is equal to phi, and A union phi is equal to A. A intersection A complement is equal to phi, and A union A complement is equal to universal set. And union universal set complement is equal to phi, and phi complement is equal to U. Power set, if A is a set, the power set of A denoted by PA is a set of all subset of A. Since phi contain A, we conclude phi belongs to PA and A contain A implies A belongs to PA. If A set A has element 0, 1, then power set of A is equal to phi 0, 1, 0. And we are theorem, if A is equal to set of n elements, then power set of A is equal to 2 to the power n. Next, prime and composite number. Prime number and integer n is prime if and only if n greater than 1 and for all positive integer r and s. If n is equal to r dot s, then r is equal to 1 or s is equal to 1. And composite number, if n integer n is composite if and only if n greater than 1 and for all positive integer r and s. If n is equal to r dot s, then r not equal to 1 and s not equal to 1. Every natural number greater than 1 is either prime or composite. Who is the only even prime number? Relation on a set, let we have a two set A and B. Binary relation R from A to B is a subset of A cross B. If A is equal to B, then we say R is a relation of A. Given an ordered pair XY in A cross B, X is related to Y by R, written XRY, if and only if XY belongs to R. Binary relation, let A is equal to 1, 2 and B is equal to 1, 2, 3. Define the binary relation from A to B as R is equal to XY, X belongs to A, Y belongs to B, and X minus Y is even. What is R? 1, 1 applies to 0 is even. 1, 2 approaches to minus 1 is even. 1, 3 approaches to minus 2 is even. 2, 1 approaches to 1 is even. 2, 2 approaches to 0 is even. Approach to minus 1 is even. So hence R is equal to 1, 1, 2, 2, 1, 3. Graph of a relation. This equation is a circle. X square plus y square is equal to 1. And this is the graph of this equation. And arrow diagram 1A, 1B, 2B, 3A. तो one approach करा one A को and one B को, 2A and 3A. Function on general set. A function f from set x to set y is a relation such that each x in x is related to a unit y in y. We denote this function as f of x equals to y. We call the set x the domain of f denoted by f, and the set y is the range of f. Denoted range of f. The set of actual element of y that appears as output of f is called image of f, denoted by image f or fx. Diagram of functions. So x, we have two set x is equal to 1, 2, 3, 4, and y is equal to ab. A function है one approach करा 2 को and 2 approaches a, 3 approaches b, and 4 approaches b. So we have a diagram, 1 approaches to a, 2 approaches to a, 3 approaches to B, 4 approaches to B. And second, x is equal to 1 to 3 and y is equal to AB. And function f of a is equal to a. Means all elements are approach to a. So 1 approach a, 2 approach B, 3 approaches a. Relation which are not function. The following is an example of a relation that is not function. F of r approaches to r given by f of x is equal to minus square root of x squared. Not defined for any value in the domain. Here is the another relation that is a function set of rational number to set of integer given by f of p of q is equal to p. 1 by 2, 2 by 4 is equal to, but 1 f of 1 by 2 is equal to 1, f of 2 by 4 is equal to set. One-to-one function or one-to-one function from set x to set y is a function such that each x in x is related to a different y in y. More commonly, we can restate this definition as f of x approaches y is 1, 1. If f of x1 is equal to f of x2 implies x1 is equal to x2, or f of x1 x approaches to y is equal to 1. If x1 not equal to x2 implies f of x1 not equal to f of x2. Here is the example of function is 1, 1 or not. So we have f of r approaches to r, set of the number to the number given by f of x is equal to 3x plus 7. We prove that f is 1, 1. Assume that f of a is equal to f of b so that a is equal to b. Now f of a is equal to f of b means 3a plus 7 is equal to 3 plus b plus 7. So 3 is equal to 3b, therefore a is equal to b. And this is the example which is not 1, 1. F of r approaches to r given by f of x is equal to xk, not 1, 1. Since 9 is equal to f of 3 is equal to minus f of 3, but 3 not equal to 3. So this is not 1, 1. Onto function of function f x approaches to y onto if for every y in y there is an x in x so that f x is y. This can be restated as a function is onto when its image equal its range, that is f x is equal to y. There is the example diagram. 1 approaches to 0, 2 approaches to 1, 3 approaches to 1. And this is not onto function. 1 approaches to 1, 2 approaches to non-element, and 3 approaches to non-element. So that means 3 approaches to 1. Here is a 2 has no image in this domain and 4 has no image in domain. So this is not onto function. And thank you.